Hello, I'm Siang-Yun Li from EPFL, Switzerland. In this video, I'm presenting our paper entitled Boolean Rewriting Strikes Back, Reconvergence-Driven Windowing Meets Resynthesis. Boolean rewriting is a classical technology-independent logic optimization algorithm dates back to 2004. By technology independent, I mean that we are working on a simple abstract model of digital circuits like the N-inverter graph, such that it is independent of the circuit implementation and will later be mapped into a technology-dependent representation using the standard cell library of a specific technology. Boolean rewriting optimizes a logic network locally by enumerating cards for each node and looking up in an optimized database. With Moore's law coming to an end, one way of keeping up with the growth of design complexity is to strive for better optimization quality in logic synthesis. However, there are two bottlenecks preventing us to extend this kind of card-based rewriting to beyond 4 input cards to get better quality, namely card enumeration and construction of the database. In this work, we try to surmount this limitation by, first, using one good window for each node instead of a lot of cards, where we propose a new idea of windowing called Reconvergence-Driven Windowing. And second, we replace database lookup by a heuristic resynthesis method. Combining the two of them, we call our new algorithm window rewriting. Compared to the state-of-the-art rewriting implementation in ABC, we obtained not only better optimization quality, but also faster runtime. There are 3 main stages in the hardware design flow. First, high-level synthesis works on the register transfer level. And then logic synthesis optimizes technology-independent logic networks. And finally, physical design produces placed and routed layouts. Boolean rewriting is a technology-independent logic optimization algorithm. It is applied on an abstract data structure modeling digital circuits, such as N-inverter graphs and XOR AND inverter graphs. It is an early step in logic synthesis, which will be followed by more fine-grained optimization and finally technology mapping. It can also be used as a preprocessing step in verification to simplify the circuit. In this talk, we will focus on area minimization, where the area is approximated by the number of logic gates, or nodes, in our terminology. The idea of the classical card-based rewriting is as follows. This is a circuit that we want to optimize. First, we choose a pivot node in the circuit. Then we enumerate the k feasible cards for this node, where k is typically set to 4. A card is a set of nodes that supports the pivot node, and a 4 feasible card is a card with at most 4 nodes. Then we simulate from the cards until the pivot to get the local function of the pivot in terms of the card nodes. With this local function, we can look up in the database with optimum implementations of every 4 input function to find a better subcircuit for one of the cards. Finally, we replace the subcircuit with the optimal one and choose another pivot to optimize. The 2 bottlenecks of card-based rewriting relating to the card size k are, first, the number of k feasible cards per pivot node grows exponentially with the value of k. And second, the number of all k input functions is also exponential to k, such that the construction and storage of the database become difficult for k larger than 4. Although there have been some attempts to bypass these limitations, in practice, it is still hard to improve the quality of rewriting without suffering from a higher runtime. The idea of reconvergence-driven windowing is to use one good window instead of many cuts. In the classical cut-based rewriting, a cut is only computed for a pivot node. In contrast, a window can have multiple outputs, and every node in the window can potentially be optimized. But what kind of windows are good? With some theoretical arguments in the paper, which I will skip here, we argue that reconvergence is essential for logic optimization, and so a good window should be a window that captures reconvergence. Given a pivot node and two parameters k and l, our reconvergence-driven windowing algorithm aims at constructing a window around the pivot node with at most k inputs and reaches reconvergence within L steps. First, starting from the pivot, we do a breadth-first search towards its transitive fan-in to find a reconvergence. A reconvergence is two paths starting from the same node and ending again in the same node. Then, we collect the side fan-ins on the reconvergent path to form a set of support. If the support size is not larger than k, then we can expand towards transitive fan-in to try to include more nodes in the window without exceeding the limit of at most k inputs. And we also try to expand towards the transitive fan-out to collect those nodes which are completely supported by the window nodes. Finally, we identify the window outputs, which are the nodes with fan-out outside of the window. We did some experiments to test the quality of our windows. First, we found that 98% of the nodes in the circuit are considered at least once in a window. And second, we found that on average, each 6-input window captures 41% of the pivots for cuts. This percentage may sound low, but in fact, the other cuts may be contained in another window, so we conjecture that the real for-cut containment should be much higher than 41%. To get rid of the exact database, we propose to resynthesize node functions on the fly. The resynthesis problem is formulated as follows. Given a target function and some divisor functions, we want to find a dependency circuit to reconstruct the target function from the divisor functions. The first part of this algorithm is similar to enumeration-based resubstitution. However, we are no longer limited to small dependency circuits because we construct the circuit recursively. This algorithm is a fast heuristic. It is not guaranteed to always find a solution, nor is it guaranteed to find the optimal solution. Nevertheless, it is general, and as long as the functions can be represented with truth tables, their input size is not limited. An important concept in this algorithm is the notion of unateness. We define positive and negative unateness for divisor functions in terms of the target function, which is different from the usual definition of unateness with respect to a variable. Suppose the rectangle is the input space, the black dots are the onset minterms of the target function, and the white dots are the offset minterms. In the other space where there is no dot, there may be don't care minterms. I will draw divisor functions as circles. They are completely specified, and the circled regions are where they output 1. This first divisor covers only onset minterms, and we say it is positive unate. Similarly, we say this divisor is negative unate because it covers only offset minterms. If a divisor covers both onset and offset minterms, we say it is binate. In this algorithm, unate divisors are preferred. If a positive unate divisor covers all of the onset minterms, then it implements the target function directly, and we call it a zero resub because it has 0 gates. If the union of two positive unate divisors covers all of the offset minterms, then an OR gate implements the target function, and we call it a one-resub. Similarly, two negative unate divisors can form a one-resub with an AND gate with negated inputs, if the intersection of their complements does not contain any more offset minterms. To recursively construct a larger dependency circuit, we choose an unate divisor to divide the target function. Suppose that we have these three divisors. D1 is negative unate, D2 and D3 are binate. We can use D1 to divide the target F. By ending with not D1, we get a remainder function F prime, where the three offset minterms covered by D1 are removed. Now, with less minterms to consider, the new target function is easier to implement. D2 and D3 now become unate, and simply ORing them together realizes F prime. To evaluate the quality of our heuristic resynthesis, we compare the synthesis results of all 3-input and 4-input functions against the optimum solutions generated by the exact method. The results show that the heuristic is capable of synthesizing most functions, and the average size overhead is 0.35 more gates per 3-input function and 2 more gates per 4-input function. Note that this experiment solves a special case of the resynthesis problem where only the primary inputs are provided, but not divisors with arbitrary functions. It would be impossible for an exact database to have solutions for all possible instances of the generalized resynthesis problem. Combining reconvergence-driven windowing and heuristic Boolean resynthesis, our new window rewriting has two main features. It constructs only one window per pivot node, and it optimizes the window by resynthesizing every node in it. In our experiment, we compare window rewriting against the state-of-the-art rewriting command, DRW, in ABC. Note that there are some other rewriting commands in ABC, but because DRW is the best among them, we only show the comparison with DRW here. In this red box, we see that running window rewriting for only one iteration, it already outperforms DRW run repeatedly until convergence. It is 3.2% better in quality and is 2.7 times faster. The implementation is available in our open source logic synthesis library, MockTurtle. Now I will do a quick demonstration of the experiment on one benchmark. First, let's try ABC with command DRW and repeat it for several times. The circuit size reduced about 700. MockTurtle is an open source library and can be downloaded from GitHub. Here I will quickly write an example code to run the window rewriting algorithm. MockTurtle can be built in any environment using CMake. Now, comparing the results, we can see that window rewriting minimizes the circuit size more with faster runtime. In conclusion, window rewriting uses one 6-input window instead of many 4 cuts. Our windowing algorithm is designed to capture reconvergences. We use heuristic resynthesis for optimization instead of looking up in an exact database. The resynthesis algorithm does local computation, and so it has the potential for parallelization, which is more difficult for database lookup because sharing of the large database among all threads will be a problem. For future work, it is possible to combine heuristic resynthesis with other algorithms. And conversely, we are also developing different resynthesis engines to be combined with the window rewriting flow. Thank you for your attention.